I also wanted to emphasize that if you are interested in running simulation of wastewater treatment plants, here we have the scheme of a plant, like the activated sludge here, primary clarifier, secondary clarifier, anaerobic digestion plant here. And so Victor mentioned the ISM and ADM1 models, so don't bother to program this. It's there's a code which has been benchmarked, and it's freely available for all this process connected to each other. So it's quite easy now to have, if you're a student, to implement and to test your controllers or software sensors. And Jorge also said that you want to give value to our waste. So it goes for circular aspect, circular economy. And it could be gas, liquid, or solid. You want to play here and to make high value molecules, fertilizers, energy, or water, and recycle all of this. This is again what I said before, the environmental biorefinery framework. I will not come back to this. What I want to emphasize is nowadays wastewater treatment plants are not called WWTP anymore. They are called water resource recovery facilities, which is what is important is recovery, and what is important is facilities, because again, you don't handle a plant like this as one process. You handle it as a plant-wide process, plant-wide combination of process. Just an illustration, this is a classical scheme of wastewater treatment plants. As you can see here, they consume energy. Here you have for 100,000 equivalent inhabitants, how many electricity you have to use per year. So you consume about 20 kilowatt-hour per year and per inhabitant. And if you design the process differently and you recover the maximum of COD from the beginning, you can gain energy. And so you can have an energetic balance, which is positive, which is very important. As I said, 3 to 5% of the energy of one country being consumed, and you can produce 3 to 5%, just changing the design of the plant. I wanted to show you here these results. This is results obtained by Hugo Mendes when he was doing his PhD with us. And I just realized that we never publish his results. So if you see Hugo somewhere, tell him that he has still a paper to publish. It's a little bit old, but it's still okay. I mean, no control. So you see the volatile fatty acids, which was a control objective here. And after we turn on controller, and in red you have the set points that has been changed, and you can see that you can regulate very well the VFA in a broad range of concentration from 0 to 3.5 grams per liter, and it's very efficient. If you're interested, there's a paper we published like 6 years ago now on instrumentation of control of anaerobic digestion, and Victor and and Hugo were involved in this paper. So if you're interested, it's a nice paper, I think. Victor also asked me to make a summary of what I knew, what I've been doing over the last years. I realized that this paper was published 15 years ago, and it was a lesson learned for 30 years ago. So I felt old when I put this paper, because now it's 30 years ago I started. But these are my view of controllers being applied to biological wastewater treatment plants. The main message is some perform very well, no doubt about it. Here you have the PhD of Victor Alcaraz. But in terms of, you have to combine this with mathematical complexity being associated to the controller, and is sensor complexity also that you have to deal with. And if you want to go in practice, well, you have to be sure that the engineer and the technician in charge of the plant will be able to manage it. And that's one point. The second point is, I'm used to say that you need to be, quote unquote, in love with the process you want to control, or at least to understand it very well if you want to make nice controllers. That's a very important point. It's not because you're the best control guy or the best mathematician that you will get nice results that will be able to be applied in practice. So you have to talk to biologists, you have to talk to people involved in running the plants, to be sure that what you do, it's what they want you to do. There are some still remaining questions and many, many challenges. Some examples here. What are the limits of the system we want to tackle? Is it plant-wide? For sure, it has to be plant-wide, but up to where? Should we include rivers, because water goes to rivers? Should we include weather forecast, because weather forecast, I mean, rain will impact what you get at the plant? Should we include microbial diversity? Should we include micropollutants, some environmental impacts like N2O emissions? How reliable are the sensors? Sensor can be managed also in terms of sensor networks. How do we do this? Big data, this has to be managed to get the most of information we can. What kind of model should be used? Static, dynamic, black box, etc., etc. An important point is sometimes we design models where everything goes well. If you combine this to a car, for example, it's like if you design the GPS of a car to tell you where to go. The problem is when you have an accident, what is very useful is how to rebuild the car, to use it afterwards. Because if you have a crash in a wastewater treatment plant, well, it will take a few months before you can restart the plant. And what do you do for a few months without any treatment? Does it go directly to the river? So models being able to tell you what to do when everything goes wrong should be very useful. That's one point I'm really pushing forward to this. How to calibrate models, how to handle uncertainty, simulation platform. I mentioned some of them. Are they enough? Do the answer ever need in practice? How to calibrate the model behind? Going from WTP to WRRF implies new paradigms. So how do we adapt control there? Actuators. 30 years ago, the main problem was sensors. Now sensor is more or less solved, but actuators, well, you cannot store wastewater coming to a plant forever. So you need to deal with this, and you don't have too many actuators. And that's an issue also. Diagnosis, it's not an easy task. How to make decisions, how to take good decisions, and how to make new applications in terms of sewer control, drinking wastewater treatment plant, water distribution network, and so on and so forth. With this, I want to thank you for your attention, and if you have any question, I would be very, very pleased to answer. Thank you very much. Muchas gracias.
Thank you very much, Philippe. Merci. Very interesting talk. And okay, we're waiting for some questions from the audience. At the moment, I have a question concerning or regarding your experience in benchmarking. Could you comment some aspect of your experience in benchmarking with water thermal plants?
In practice or in simulation?
both.
So in simulation, I strongly advise you to use code which has been validated. What I mean behind this is, I mean, many years ago now, we had a European project to compare control strategy for wastewater treatment plants. And we were 14 groups all over Europe. And so what we did first is, okay, we took the book of the ASM model and we said, okay, everyone will implement it, and after we will test control strategies. And one guy, I remember one guy said, well, what if we benchmark our code? What if we say, okay, with constant inputs, we should have the same output? And it was a big surprise for me because out of 14 groups, we got 9 different steady states. It was because of plus instead of minus. It was because of the way it was calculated. Some stupid points, but which were affecting the results at the end. So nowadays, all the wastewater treatment plants models, like ASM, ADM, whatever, are implemented in different platforms, in different codes, source code like Fortran, C++, MATLAB, Scilab, or whatever, and they have been benchmarked. So in terms of simulation, I strongly advise you to use them, and they're for free, which is good. In practice, it's another story. In practice, since you deal with living organisms, it's difficult to compare. And it's difficult to compare because the performance can change according to what you've been doing to the plant or to the microorganism before. And so it's quite different. It's quite difficult to benchmark. And what you have, I mean, my experience is to benchmark it over a few weeks instead of few hours. If you have a similar result, more or less similar, over a few weeks, well, you can compare them. For a few hours, it's not so easy.
Victor, may I ask something? Yeah, Jean-Philippe, thank you very much for this very interesting presentation. And I'm wondering if we look to, or what would you say are the biggest challenges when we look to wastewater treatment processes in climate areas where you have high humidity, where you have high temperatures, where you have high load of organics in the influent? What are the challenges for I know we know a lot of biological kinetics and processes, but I think the most, maybe you can agree on that, the most challenge here is for the controlling and the technical implementation, and this should correspond with the model response, in order to achieve a good treatment results in these climate areas. What are the biggest challenges here?
What do you mean by climate?
Yeah, when you look to climate zones near the equator, for example,
Okay.
when you go to Africa or to Asia, where you have high temperatures, sometimes 38, 39 degrees, 80, 90% humidity, and so on, and very high loads of organics in the wastewater.
For me, it's a question of the ratio between organics and like carbon and nitrogen and phosphorus.
Yes.
What people think from scratch is to say, okay, I will design a classical activity sludge process. And in fact, it's not when you have high temperature, it's not always a good solution. In Brazil, for example, many plants are based on anaerobic digestion. where you decrease the organic load, and after you can recover also nitrogen and phosphorus to put it in the field. So if you're in Norway or in Finland, well, this is not adapted because it's too cold. But if you're close to equator, anaerobic digestion can be a solution, and you can produce energy also. And as I said, you can recirculate nitrogen and fertilizers to the field. The main point there is you have to deal with chemicals and micropollutants and microbial aspects. You have to be sure it's safe. But I know many plants in Africa, in Brazil, in Chile also, where they use anaerobic digestion upfront to decrease the load.
Yeah. Yes, as far as I know about these kind of or these treatment plants you can find in these areas, they often have to fight with instabilities. Instabilities according to biological degradation and caused by high dynamic of organic pollutants you receive from the households or from industry. So it's a big challenge, and you talked about the robust systems. What to do if a wastewater treatment plant fails, and in these countries you will have very often this situation. So I think that modeling and models will face a big problem in this case.
But it's already 15 years ago now. We were involved in a European project with Victor and Victor in Mexico for tequila wastewater industry, and this is manageable. But I fully agree. It has to be. I mean, it has to be controlled in one way or another. If you compare to methane production, it's like a cow. If you give it no food or too much food or not the good food, well, the cow will not be very happy. The same with a digester. It's a living organism, and if you manage it efficiently, you will get nice results. But again, compared to activated sludge, people say, okay, anaerobic digestion is good because it produces less sludge, like 5 to 10 less sludge quantity per kilogram of COD removed. But if you produce less sludge, you're also slower. So to start up a process, it takes time. But you can have some modularity in the design of a plant. It's feasible, but it's not for free. I agree.
Yeah. Okay. Victor, we have one question in the chat. Shall I read it?
Yes.
Just the question is from Carlos Ortiz. To you, Jean-Philippe. Considering that one of the relevant parameters for sanitary water discharges, as regulated in most Latin American countries, is BQDO, biochemical demand of oxygen. Why to run the process controls and the effluent parameters versus nitrogenated compounds and volatile fatty acids only?
It was just an examples I gave with volatile fatty acids or nitrogen, but for sure, VFA or what, I mean, not ammonia, but it's related to biochemical demand of oxygen. It's related to this, but you have, I mean, a wastewater treatment plant is designed for 20, I mean, at least in France or in Europe, is designed for 25 years, more or less. And after, I mean, some years ago, regulation was evolving. So it was designed for COD removal, and after you added a plant for nitrogen removal, and after for phosphorus removal. But for nitrogen removal, you need COD. And I know some plants that were buying COD because they were decreasing too much COD as a first process. which is kind of stupid because you have COD and you eliminate it, and after you buy external COD to make nitrogen removal. Well, that's what happens sometimes. But again, it was just example I gave for ammonia or VFA. But again, you have to design. It's not one process. It's a combination of process you have to deal with, and couple processes. And this is what is challenging for me because you have different dynamics, you have different objectives, and you have to manage all of this at the same time. But that was that was a good question.
Okay. Okay, Victor, I think we are so far through with questions, so we can, my suggestion, come to the next presenter.
Okay. Thank you very much,
Thank
Philippe.
Bye-bye.
Okay, the next presentation is by myself. I'm going to deepen a little bit on some specific aspects regarding monitoring of wastewater treatment plant by state estimation. Please, Andreas, can you share
Yes,
the
yes.
presentation?
Wait a minute. Okay, here we are.
Okay. In this talk, I will show you some application examples of state variable estimation, input estimation, and kinetic estimation. And in all of them, I will take as target process the anaerobic digestion, but the applications can be also used for any other wastewater thermal process. Next, please. As I said, this is the model AM2 for anaerobic digestion. I recall that this model, in this model, X1 and X2 represent the two main microorganism groups. S1 and S2 represent the two main substrates, that is chemical oxygen demand and volatile fatty acids. And the other two variables are the total inorganic carbon and the strong ion concentration respectively. Next, please. On the other hand, I start by giving a simple definition that what estimation theory means. Basically, it consists of estimating known parameters and or state variables from a set of measured state variable ones. In the case of variable estimation only, they are named software sensor or observers. And maybe the two best known and used ones are the Kalman filter and the Weinberger. They are.
¿Estoy conectado o no me puedo conectar?
Sorry?
No,
Victor,
go ahead.
Okay, thank you. There are others like the high gain observer and the sliding mode observer. And we have also the asymptotic observer, the interval observer, the unknown impulse observer, and the virtually controlled observer. Next, please. Okay, regarding the Kalman filter, it basically consists of the following. We consider a model in ordinary differential equations representing the dynamic behavior of the state variables. We have also a model of the measurements that, yes, and we consider that both the state variables model and the measurement model are provided with a term that compensates model errors and measurement noise, respectively, and that these terms have a Gaussian behavior. Next, please. Thus, the Kalman filter for estimating state variables, both measured and unmeasured, is built by taking the dynamical model without the error terms, but adding this another term one in equation 36, which is a function of the actual measurements, the measurement model, and a term named gain, this K matrix, that is calculated on the basis of the dynamical statistical behavior of both model and measurements, here represented by the matrix P, named covariance. Next, please. In turn, the Bloomberg observer has exactly the same structure of the Campbell filter, that is reproducing the dynamical system behavior, plus again term like you can see in equation 39. Next, please. And the difference between the two observers is that the gain matrix is in the Bloomberg observer case is calculated in order to assuring convergence and stability properties of the estimation error dynamics. Next, please. So the following is a real application example of the Bloomberg observer in an anaerobic digester in order to estimate the complete volatile fatty acid production and consumption kinetics function for controlling this variable, volatile fatty acid concentration, around a given reference function. Next, please. So in the top of the slide, you can see the control algorithm needed. That is a function of this unknown function representing the kinetics and containing monod and Haldane material raw kinetics terms. This is the variable that we want to estimate by using the Bloomberg observer. And then here also the graphics, you see the system of this function in the bottom, given by the Bloomberg observer. In the right, in the top, the input flow calculated by the control approach in gray, and the actual flow given by the pump, that is drawn in blue. And here below, how the volatile fatty acid concentration in blue is effectively regulated around the reference function drawn in gray. Next, please. Now I want to describe another observer, which is fully independent of the knowledge of kinetics. It is it's called the asymptotic observer. For doing that, I recall that chemical and biochemical processes can be described by a general model or a standard model with the following standard form. The first part represents the nonlinearities, that is kinetics. In the middle, we have the terms that are representing the linear part of the model. And B vector is one vector containing process inputs and other state variables independent terms. The state space can be split in such a way that the model can be rewritten as in two equations in the bottom, where x1 is a vector representing, capital X1 is a vector representing the state variables that we can measure and that we want to estimate, and capital X2 is a vector containing the state variables that we can measure. Next, please. Then, in the following, we perform a state variable combination like this in order to have another auxiliary variable, small w, whose dynamics is a function of the original state variables that are effectively measured, and then the reconstruction, and therefore the estimation of the unmeasured variables, is given by inverting the linear state combination like in the third part of the the TIR equation. And we focus also in the fact that this asymptotic observer is fully kinetics independent. So this is a very interesting feature of this observer that allows us to avoid this uncertainty source. Next, please. Here you can see experimental results of steady estimations, once again in an anaerobic digester, where by using online measurements of chemical oxygen demand and volatile fatty acids, it was possible to reconstruct the total inorganic carbon concentration and strong ions concentration, validated with online independent measurements in black in the bottom of these graphics, as well as to estimate the concentration of acetogenic bacteria and methanogenic archaea, the first two graphics at the top. Next, please. Now, if the uncertainty source comes from processing inputs, it is possible an interval observer under the same structure in which the maximum and minimum process input values, partially known, are used for estimating a warranty interval in which the estimate state variables can evolve. Next, please. Here you can see an experimental example in which hypotheses on process input concentrations are only validated by online discrete measurements at the top left side. We have also online measurements of the dilution rate, the total inorganic carbon, biogas flow, and volatile fatty acid concentration. And with this partial information, it was possible to estimate intervals on COD and strong ion concentrations. Here validated as well in the bottom, in the graphic in the bottom, with online independent measurements. You can see that effectively the actual measurements of the chemical oxygen demand and strong ion concentrations are into the estimated interval. Next, please. And finally, an example of how the asymptotic observer can be used for estimating process inputs. It is a virtually controlled observer. In this graphic, let's assume that we dispose of the two measurements of one state variable, let's say the chemical oxygen demand, here represented by capital S1, and that assume also that at the same time we are estimating it, this variable, with an asymptotic observer on the basis of hypothetical but uncertain input concentrations. So, if the estimation error is not zero, then a virtual controller provides the asymptotic observer with improved hypotheses on the process inputs until obtaining convergence. Next, please. In this experimental results, we see the variables used as measurements, the dilution rate, volatile fatty acids, and total inorganic concentration. Next. And here the estimation performed by the virtually controlled observer on the chemical oxygen demand and strong ion concentrations. In gray, the estimation given by the observer, and in solid black, the measurements showing relatively very good convergence. Next, please. And therefore, by using this approach, here you can see the very good estimation of the volatile fatty acids and the chemical oxygen input concentrations. Okay, I think that's all. Thank you very much for listening, and I will be happy to answer your questions. Thank you.
So there are no questions so far. Maybe too much mathematics.
Sorry. So for mathematics, I try to do most as possible of form of algorithms showing more experimental results and examples, but
Yeah.
yes.
Okay, Victor.
Thank you very
So
much.
no questions.
Okay, next presentation maybe will be more digestible or digestible, maybe. I don't know. And the next presentation is held by is about just nonlinear control approaches in wastewater treatment plants. Please, Victor, the floor is yours.
Okay, thank you. Thank you very much to Dr. Alcaraz and Professor Pastrick for the invitation. I would like to thank also the audience from the graduate program in chemical engineering at CUSEI, at University of Guadalajara. And I'm also see that our Brazilian colleagues from Swindon, Latin America, are in the audience. So, bem-vindo, brasileiros. Jean-Philippe Steyer made a beautiful introduction and of what's going on the modeling and of course the future of wastewater treatment facilities. I like that very, very much. He makes my presentation easier. But I have to say that selling a control project is very, very difficult because involves the purchase. We have to buy sensors, we have to buy actuators, we have to convince the owners of these industries to invest in the implementation, application of the control schemes. I remember one slide that Jean-Philippe showed us. It was about the mathematical structure of the advanced control schemes. So what we are doing, or what he had done in the last decade or so, is to develop advanced control schemes that can be easily implemented and easily understood by a regular, normal control or process engineer. And in this case, in the tequila industry. Okay? Because as I said before, we can talk about different names: stochastic control, adaptive control, nonlinear, robust. So for a normal control engineer or technician, it will be different, very difficult to communicate. So what we did with some friends, some researchers from the Autonomous University, Metropolitan Autonomous University in Mexico City, and one of the PhD students who is now working at the University of Kiel in Germany. What we did was, okay, we want to solve a control problem. Okay, but we want also to explain it, you know, like a 10-year-old kid, just like Groucho Marx said a long time ago. But what we wanted to do was to apply it, to implement it, to solve a problem. Okay. When we try to sell these approaches, advanced control approaches, is that first we have to solve the environmental problem. Okay, that's the main objective of our research program. We have to focus on solving
Victor, just to mention, if you want me to show the next slide, please tell me, yeah?
Yeah, sure.
Okay.
Okay. And then we have to tell the people from industry that they will have also an added value product, which in this case is the production of the so-called biogas, which is a mixture of methane and CO2. Okay, next, please. Next slide, please, Andres. Jorge also showed some data about the tequila production. Okay, this is, with no doubt, the most known alcoholic beverages from Mexico. That's it is increasing. The production is increasing at least 10% per year. But the problem here is that for each liter of tequila produced, tequila factories generate 10 liters of vinazes, or wastage that are extremely pollutant. Okay, the range of the BOD, biochemical oxygen demand, is really high, is at least 10 times as high as the domestic wastewater. Okay, and in addition, the Mexican government has strengthened the ecological laws about the disposal and treatment of tequilaminaceae. Next, please. Both Janfi and Victor Caras has shown the processes that are involved in the anaerobic digestion. And Jean-Philippe also show that the International Water Association has developed, or they have a benchmark model to test both the state estimators and controllers for a, for a better understanding of what's going on in these transformation processes. The typical anaerobic digestion involves these four steps: hydrolysis, acidogenesis, methanogenesis, etc. Next, please. One of the main problems about treating vinases, any kind of vinases, is that we have not only to control the chemical oxygen demand, we have to take into account the content of volatile fatty acids. The accumulation or the excessive accumulation of volatile fatty acids may lead the digester to a breakdown. That phenomena is called the washout, where the microorganism population died. Several approaches, of course, have been applied, developed over the years, from the classical textbook proportional integral and proportional integral and derivative controllers to regulate pH, COD, and biogas production. In the last 3 decades, other groups, research groups, have applied different approaches. Okay. In this particular application, we use an advanced output feedback controller with input saturation to provide asymptotical stability. Let me say a little bit about input saturation. This with with this feature, we take care of some practical problems that are very common in practice. We don't have an infinite capacity to change the flow rate in a system. So they are constrained, they are bounded by physical limitations. Next, please. Here, we use the ADM, anaerobic digestion model 2, which involves two main reaction steps. Is the acidogenesis and the methanogenesis. In the first step, the organic matter is transformed into volatile fatty acids and some other products. And in the second step, the volatile fatty acids are decomposed into the biogas, methane and CO2. The model is derived from the mass balances of the species involved. The organic matter, biomass 1 and biomass 2, which are the bacteria in the first step, and the archaea in the second step. We use typical kinetics. For instance, in the first reaction or biochemical reaction, we assume that the kinetics are expressed as a monode kinetics expression, while in the second is the Haldane, which includes a term for product, or for substrate inhibition. This in this expression, okay, we include the effect of the accumulation. I mean, the inhibition leads to accumulation of volatile fatty acids. The approach that we use comes from the analysis of changes of operating conditions. These are resumed in the so-called bifurcation diagrams. We have the dilution rate, which is the reciprocal of the residence times, which is related to the feed flow rate, which is, in this case, is the variable that we have to change, that we have to manipulate to achieve the desired value at the end of the bioreactor, at the end of the digester. Analysis, we can see the interval of the manipulated variable, which in this case is the dilution rate. So we set the limits of these variables that can be operated to operate the system under normal conditions. Okay. Next. With this in mind, I will skip the mathematical manipulation of this controller, and just say that the control action is or can be reduced to use the minimum dilution rate, the maximum, and of course, the calculated from the dynamics of the model. Okay. One thing that we can do is that mu, which is a nonlinear function, is given as a observable or measurable variables. Next. Please continue to. Okay. What we wanted is to implement this in practice, okay? And if we show the equations that I mentioned earlier, it will be really impossible for the process engineer to understand what we would like to show everybody. So we set a number of guidelines to tune the controller. Okay. We set the limits theoretically, yes, by analyzing the bifurcation diagram. And then we started a tuning process like is a textbook classical control tuning technique. Okay. So we talk to the process engineer and says, okay, you have to do this, but you have to do it in simulation because it will be easier and of course cheaper. Okay. And in the application, we started with the resulting parameters, K and omega. Okay. And then changes a little bit. Very easy guidelines to follow. Okay. Next, please. These are the characteristics of the experimental setup and, of course, the binases. We use raw tequila binases. most of the tequila factories that they have wastewater treatment plants use soluted tequila vinases. We wanted to show that if they dilute the vinases, it will be more expensive, the treatment, the wastewater treatment. So we use raw tequila vinases. Of course, we tested in a pilot plant for 445 liters, a fixed bed package bioreactor that we have, I could say. Of course, as Jeffrey said, the more information we have about the process is better. We can design better control schemes. So we have measurements of volatile fatty acids and bicarbonate concentrations and partial and total alkalinities. And also we have measurement of the biogas flow and composition, online composition. We use a standard data acquisition system, and we connected the system to a computer using the LabVIEW setup. In this particular case, the output feedback controller aims at minimizing the volatile fatty acid concentrations. So we set the PFA as the output variable, and the feed flow rate is the manipulated variable. It is here. I did a mistake. Is the input variable. Next, please. This is the experimental setup, how we have the pilot plant in our lab. It's fully instrumented with different sensors that are all connected to LabVIEW. So we can, we not only send them to our computer, because this system is connected to internet to different research groups in France, particularly at LBE in Narbonne. We share this information with Janfi and another colleague of us, Eric Latrier. So we can monitor, we can see what's going on 24/7 around the globe. Next. To closed loop simulations, we found these parameters for the implementation of the controller. Next. Okay. What we wanted in this presentation was to show the process engineers at the tequila factory. The tequila factory is located 45 kilometers from Guadalajara. is that we're gonna test, or we wanted to test the controller under actual or realistic operating conditions. That means that we will run the experiment even in the face of sensor failures or dramatic changes like no power, no electricity. Okay. So we set the reference signal, the set point of the volatile fatty acids concentration. So we run we close the control loop. We run the experiment. So at the very beginning, we have some problems that lead us to return manually the control parameters. Okay. After we have a reasonable good response, we tested our scheme by changing the set point. This is typical in control engineering. So we need to check if the controller adapts to set point changes. As you can see, reaches the set point satisfactorily. Next, please. Here, we show the effect of typical realistic failures. Okay, the NSense, which is the device to measure alkalinities and volatile fatty acids. We have a problem with the interface. The operator, by mistake, turned the lights off, and we have a problem. We have a electric shutdown, but in any case, in the face of these failures, the controller compensated all these problems to yield a good performance. Next, please. Well, I just said that we test the controller in a real scenario, operator mistakes, which is very common, sensor failures, devices, of course, the typical changes to test the robustness of the controllers or the bus controllers, and the problem related to the miscommunication between the pilot plant, the data acquisition system, and the laptop. Next. Before I close this presentation, let me remind that Carlos Ortiz asked about typical control approaches in the Mexican industry. He mentioned about the biochemical oxygen demand. If we try to meet a certain value on the BOD, we have to take into account that reliable readings of the BOD takes at least 5 days. Okay. This delay, it is very difficult to take into account in any control technique. Instead, we use chemical oxygen demand, which is easier and faster to measure. But even in that case, it has a sampling time which may cause some instability problems. We have done a different approach based on the same output controller, and we change it to what we call a cascade control. A cascade control is a controller that has two loops: an inner loop, a fast loop, and the outer loop, which is the slow control loop. In the first loop, we use online measurement of conductivity that can be related to volatile fatty acids. And in the outer loop, we use COD measurements that are taken with a certain delay, discrete, we call it discrete. So we combine two different sampling measurements. One continuous or relatively continuous, and a discrete measurement to control both the chemical oxygen demand and the volatile fatty acid. With that, we implemented in tequila vinases. In that particular case, we met the environmental policies for discharge tequila vinases in terms of chemical oxygen demand, and we prevented the excessive accumulation of the volatile fatty acids, and prevent, of course, the breakdown of the digester. To give you an idea of effect of having excessive accumulation of volatile fatty acids in an actual digester, it takes 5 to 6 months just to recover that failure. So it's very, very expensive. And we think that with this approach, which is given in textbook lines, textbook guideline, we can implement advanced control techniques. With this, I close my presentation, and I'll be glad to answer your questions. Thank you very much.
Thank you very much, Victor. There is or there are questions from the audience, please.
One short question. Okay.
Okay.
Philippe, go ahead.
Jean-Philippe. Okay.
Thank you, Andreas. Thank you, Victor, for the presentation. And I just wanted to make a comment. In 1998, a student of mine started a company to sell process control approaches to companies.
Okay.
And in fact, he sold one license of the software. He had one example, and after he stopped because he couldn't make a living out of it. In 2005, I mean 2002 to 2005, where we were involved together with an European project, we sent in France 200 questionnaires to industries having a digester to know their wish in terms of control. We got one answer. and in fact, it was too early. In 2015, a student of mine started a company. Now there are 15 people. They are selling like 50 applications of control in all over France, and they go to international now, and it's still growing. So we have to be on time in this, and industrial people, if you can show them that it's worth to implement it, they will buy it for sure.
Okay. Well, let me tell you something. We are, of course, we ask for tequila vinases. They will give us as many tons of tequila vinases that we want. Okay, but in this case, it's a tequila factory that is owned by a transnational, international company. Okay. To what we propose, because of a single opinion. The engineer in charge of the Westward okay, so he understands what we are doing, and he has
We have problem of connection, no?
Yes, we have problems with the connection. But Guido, my suggestion is because of time, we should come to closing remarks.
Okay, well, we have a promise to implement or propose controllers in a real life tequila factory. Okay.
Okay, thank you very
That's all.
much, Victor. Okay, we are conclude. Through the different talks in this webinar, we have seen several modeling and control approaches that can be currently implemented in the industry. We have the very good and valuable experience of all the speakers. And so I would like to thank once again very much to the keynote speakers for participating with all your valuable experience in this webinar. Thanks also Andres for your support. And thanks also the numerous audience for attending this webinar and for the questions and discussion that you have raised. In this way, we hope that's the profit of everyone. We conclude so this webinar, and many thanks. Thanks a lot.
Thank you much, Victor. Thank you to the audience, and yeah, stay healthy. Huh?
Yes. You too.
Okay.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Ito.